back to the random growth masterclass. So just to remind you where we were last week, we basically got to the point where we were able to construct the stochastic integral, or at least to prove the existence of the stochastic integral as a limit of integrals of simple processes. And I set you the exercise, which was to compute this integral from 0 to t of Brownian motion with respect to itself. So who had managed to do that exercise? Anybody? Did anyone try it?
Exercise session is later, so.
Well, it's in 2 hours' time with the solution. So the idea is you sort of should, in an ideal, we'll do the question. So nobody tried to do this. No? Okay. In general, just relating to the exercises, a lot of the really useful properties of these processes I've put in the exercises, so things that you'll really need to know in order to understand the random processes. So the course kind of consists of the lectures and the exercises together. So it is, I know you're busy, but it is a good idea to actually give some thought to the exercises during the week, rather than just sit in the exercise class and just have Dimitri explain it to you, because that's not kind of quite the same thing. Anyway, it's a shame that you didn't do this, because had you done it, you would have discovered that it was kind of difficult, right? Does anyone want to guess what the answer might have been for this? Any? Just any guess at all? Sorry. Right. It's not going to be a Gaussian. What if this wasn't Brownian motion? What if I just asked you to integrate x dx? What would that be? Half x squared, right? So one guess is this going to be half b squared? Now, can anyone see a reason why this isn't going to be half b squared? Maybe I'll just close the window because it's a little bit noisy outside. So what were the properties of the stochastic integral? What were some of the useful properties that we established?
Expectation.
It's got expectation 0, so yep, that's already a bit of a warning sign that, so I should have made this BT, that this does not have expectation 0, this has expectation half t. So that's already a sort of warning sign. It's not going to be that. And in fact, the most important property we have of the stochastic integral is that it's a martingale. So can anyone go for a guess how this might change into a martingale? Say again, sir?
Minus TO2.
Yeah, that's right. So, okay, and it turns out that actually is the answer, because if you remember, you proved in in one of the previous exercises that was a martingale, and so it sort of looks a little bit like it should, but it needs something extra to make it into a martingale. Anyway, as I said, if you'd done this exercise, you would have found that it was difficult. That it probably would have taken you about half a page of sort of writing this as a piecewise sum, and then taking mean squared limits of all the components, and eventually you would have reduced it to this. Now what I'm going to do today is we're going to do something called Ito's formula, which will show you that actually you don't need to go through this process every time you want to do a stochastic integral. That actually using Ito's formula, doing stochastic integration isn't that much more difficult than just doing ordinary integration. Okay, so let's start with some definitions. Okay, so the first definition is an Ito process. So an Ito process is a stochastic process of the form xt is equal to x naught plus integral from 0 up to t ys dbs plus integral from 0 to t zs ds, where x naught is the initial condition and that needs to be f naught measurable. And yt and zt are adapted and satisfy integral from 0 up to t, expected value of ys squared ds is strictly finite, and expected value of integral from 0 up to t, expected value of mod zs ds is finite. Okay, so these two, these conditions of being adapted and satisfying these sort of finite moment conditions, these have to hold in order for these expressions to make sense. In particular, remember, we only defined the stochastic integral for an adapted process which satisfied this condition. So this secondary condition is precisely needed for that to make sense. But the key point is any eta process is a process which can be decomposed into a stochastic integral and a Riemann integral. And we have some differential shorthand for this. We can write this as dxt is equal to yt dbt plus zt dt. Okay, so when you see this differential shorthand, this precisely means this, right? So I'm not talking about differentiating Brownian motion. We know we can't differentiate Brownian motion. I'm not talking about differentiating xt. In general, you can't differentiate xt either. A statement like this means precisely that I can write xt as the sum of an integral with respect to bt with that integrand and an integral with respect to ds with this integrand. So I'm going to use this differential notation a lot in today's lecture, just because it saves a lot of effort having to write these integrals. But just be careful that it doesn't sort of mess with your intuition. We're not differentiating anymore. This doesn't mean differentiating Brownian motion. This is shorthand precisely for this. So every time you see a statement like this, in your mind, turn it into its integral form, and that will explain exactly what I mean. Okay, any questions on that so far? Okay, and one other thing that we can show is, again, this was last week's exercise, which I guess nobody did, but you can show that the quadratic variation of xt is integral from 0 up to t y squared ds. Okay, and you don't exactly show this in the exercise question from last week. What I asked you to show was that if I had this expression where y was a simple function, then we had this property. Once we know it holds for simple functions, we can then take limits throughout, and so we know that the quadratic variation of this expression is exactly given by this. And now if you add a Riemann integral, we know that Riemann integrals have finite variation. We discussed this when we looked at the Riemann-Stieltjes integral, And so we know that if you have a process with finite variation, it has 0 quadratic variation. And so it's reasonably straightforward to show that the sum of a process with non-zero quadratic variation and something with 0 quadratic variation, only this bit matters. And so we get that property. And this will be something that we need towards the end of the second lecture today. Okay, so I think we're ready to write down Ito's formula. So this is probably the most important theorem in all of stochastic calculus. So if you only learn one thing, then learn this theorem. Okay, so suppose that f is a function from 0 infinity cross r into the reals, and I want this to be a C12 function. Does everyone know what this notation means? No. Okay, so this means it's once continuously differentiable with respect to the first variable t. So we've got a t variable here and an x variable here. So we want it to be once differentiable with respect to t and have continuous partial derivative, and twice continuously differentiable with respect to the second variable. Okay, so in the C basically tells you that we want it to be continuously differentiable, and these tell you how many times in each variable. So once in the first variable, twice in the second variable, and I can put other numbers there. But for this course, this is generally what we want C12 functions pretty much in everything that we do today. Okay, then what does Ito's formula tell us? Well, it tells us that df of txt is equal to yt df by dx at t and xt dbt plus zt df by dx at t and xt plus df by dt t and xt plus half yt squared d2f by dx squared txt dt. Okay, so remember xt was an Ito process. Xt was given by this expression or in differential notation like this, and I've given you an expression for f of txt. So when you look at this in your mind, turn this back into this expression. So what does that mean? Well, that means that f of txt minus f of 0 x0, or sorry, is equal to f of 0 x0 plus this integral. So instead of ys, we have ys partial df by dx with respect to dbt plus this integrand with respect to dt. Okay, so that's what this means. This gives us an expression for f of t in terms of a stochastic integral and a Riemann integral. So it's a decomposition of f of tx into these two types of integrals. Okay, and maybe it's just a little bit easier to see it in the simplest case. So in the simplest case, let's just let f just be a function of one variable. Let's just look at f of one variable and let xt be the simplest thing well, interesting thing possible, let xt just be Brownian motion. So let y be equal to 1, x0 be 0, and z be equal to 0. So then you can just see this integrates to just Brownian motion. So we just take xt to be Brownian motion. So in the simplest case, when f of tx is just equal to a function of x, and xt is just equal to Brownian motion, this gives, so this time I'll write it in the integral form, f of bt is equal to f of, well, it's going to be 0, f of b0, but we know that Brownian motion starts at 0, so that's just f of 0 plus integral from 0 up to t df by dx at bsd bs, because y is going to be equal to 1, so we've just got this, plus, well, there's no zt term because zt is equal to 0. There's no df by dt term because f doesn't depend on t, and so we just have this term, so half integral from 0 up to t, y is equal to 1, and so we just have d to f by dx squared bs ds. Okay, so this is the sort of simplest version of Ito's formula. This is the sort of most useful form of, well, one of the most useful forms of Ito's formula because it holds in large generality. Okay, any questions on just the statements that I've written here, the notation I'm using? Okay, so if we didn't have this here, that would essentially just look like what you're used to, right? That's just your fundamental theorem of calculus. So essentially what Ito's formula does is it tells us that, well, the fundamental theorem of calculus that holds for finite variation processes doesn't hold anymore. It almost holds, but we need to add in this extra sort of Riemann integral as well. Okay, so before I prove Ito's formula, I'm just going to show you a simple example. So here's an example, and we'll just use this simplified version of Ito for now. So let's choose f of x just equal to x squared. Actually, and if f just depends on x, I can just replace these by f prime and f double prime. Just makes it look a little bit less frightening. Okay, so let's take f of x equals x squared. Then what have we got? Well, f prime of x is just 2x, and f double prime of x is just 2. So by Ito's formula, what does that tell us? Well, that tells us that f of bt, well, f is just bt squared, so that tells us that bt squared is equal to f of 0. Well, that's just 0, so we don't have that bit. So integral from 0 up to t. F prime is equal to 2x, so that's going to be 2 bs dbs. Plus, what have we got here? Well, here we've got just the value 2 integrated between 0 and t, so that's just equal to 2t divided by 2, and so this just gives us t. And what happens? Well, we can actually just rearrange this. Well, this actually gives us an expression for integral from 0 to t bs dbs, and it shows that this is just equal to 1/2 bt squared minus t. Okay, and that's exactly what we would have got if we'd done the exercise from last week. Okay, but the key point I wanted to show you was, had you done this, you would have realized that it was going to take you more than half a page of sort of involved computations, And using Ito's formula, it just turns into one line. Okay, and so this is not just specific to this value of f. In general, doing stochastic integration is actually not that much more difficult than just doing ordinary integration. So let me show you what I mean by that. Okay, so suppose we want to compute an integral of the form integral from 0 up to t f of bs dbs. Oh, well, let's start with something a bit easier. Let's just start. Supposing I want to compute f of x dx. Okay, let's go from A to B. Okay, how would I do that? So what did you say? Would you compute Riemann sums? I mean, is that what you do every time you have to do an integral? Just no. So what do you do when you need to compute an integral? You look for the primitive, right, or the antiderivative. Okay, so this is actually what you do. If I give you any integral, if I say, compute the integral of sine x dx, you're not doing a Riemann integral of that, right? You're going, oh, hang on, I know that if I differentiate, minus cos, I get sine. Okay, so I'm going to write this is minus cos between my limits. Okay, so what do? We look for a function g of x, which has the property that g prime of x is equal to f of x. So that's what you do in practice. If I ask you to do any computation, you look for this function that has this property, or you put it into Wolfram alpha. But I mean, essentially that's the same thing. Well, then the fundamental theorem of calculus tells us that the integral from A to B of f of x dx is equal to g of b minus g of a. Okay, and then that's your answer. Okay, and you probably do this thousands of times, every, well, I don't know, certainly hundreds of times a month. You probably just do this without even thinking. Okay, so now let's suppose we want to do the stochastic integral. So now suppose we want the integral from 0 up to t of f of bs dbs. Okay, so we start with the same thing. So again, we just look for a function g that has this property. So again, let g satisfy g prime of x is equal to f of x. Well, let's now throw Ito's formula at g. So what does Ito's formula tell us? Well, then it tells us that g of bt is equal to g of 0 plus integral from 0 to t, g prime of bt dbt, plus half integral from 0 up to t, g double prime of bs ds. Okay, but we know what this is. This is just equal to f of bs. And this is what we were actually wanting to compute. And so rearranging, now tells us that integral from 0 up to t f of bs dbs is just equal to g of bt minus g of 0 minus half integral from 0 up to t g double prime of bs ds. Okay, and this is just an ordinary Riemann integral. So you can study Riemann integrals pretty easily. There's nothing kind of weird going on with that. And so essentially doing the stochastic integral just boiled down to the same problem, which is just trying to find an antiderivative or a primitive of f. And once you've done that, you have an expression for that integral. And this extra term, it sort of really has to be there, right? Because if we didn't have this here, we know that that's a martingale. There's no reason why this should be a martingale, right? If for arbitrary f, that gives us any sort of choices of g that can be the primitives of f. So in general, this is not going to be a martingale, and this is precisely the point the amount that we need to compensate this by in order to have a martingale. Okay, so just write that down. So it's just an ordinary Riemann integral. And it needs to be there to ensure that integral from 0 to t f of bs dbs is a martingale. Okay, so as I said, hopefully what I've convinced you of with this argument here is that really there's not a lot, once you've got Ito's formula, there's not a lot to be frightened about in stochastic calculus. So constructing the stochastic integral, yes, that was kind of difficult because all of our original ideas didn't work and we had to sort of move from almost sure convergence to mean squared convergence and use various martingale properties. So showing the existence of the stochastic integral, that's difficult. Once we have Ito's formula, then really stochastic calculus, it's only a very little bit more complicated than normal calculus. Yeah, you've got one extra term, but it's just a Riemann integral, and you can work out fairly explicitly what it needs to be. Okay, so before I go on to sort of prove Ito's formula, any questions? Okay, so let's do the proof idea for Ito's formula. Okay, so far, until we have Ito's formula, the only way that we understand a stochastic integral is as a limit of simple processes. And so I'm going to try and construct the sort of right-hand side in this way. So in particular, I sort of want some partition, which I'm going to be using to then construct my simple process. So let's just take our usual notation for partition. Be a partition of 0 and t. Right, then what we can do is we can actually write f of t xt as f of 0 x0 plus this telescoping sum from I equals 1 up to n f of ti xti minus f of ti minus 1 xti minus 1. Okay, so this is just our standard telescoping sum. All of the internal terms cross-cancel, and we're just left with the first one and the last one. Okay, so we need to try and understand what's going on over here. We're sort of assuming that these gaps between these TRs are going to be quite small. And so we want to be comparing f at 2 points which are kind of close to each other. So anyone got any ideas? What sort of results can we use to compare f at 2 points which are kind of close to each other? What if I just had a normal function and I had f of x plus h minus f of x? What would I do to try and understand that? So, just say that again. Mean value theorem, or even more, mean value theorem kind of gives you one way, but even like mean value theorem, but more. So mean value theorem expresses this in one term. It sort of tells you, well, this is equal to f prime at some value c times h. But what if I sort of wanted more than just one term? Taylor's theorem, that's right, yeah. So what we're going to do, we're going to use Taylor's theorem over here. And when I use Taylor's theorem, you'll see why mean value theorem won't work. Mean value theorem would work if these were finite variation processes. Because they're not finite variation processes, one term isn't enough. We actually need to use Taylor's theorem to two terms. So so let's write this down. So by Taylor's theorem, what do we have? We have that f of ti xti is equal to f of ti minus 1 xti minus 1 plus, well, we'll do the t derivative first. Si xti minus 1 ti minus ti minus 1, where this is going to be some point between there. So remember, we only know that f is once differentiable in t. So we're going to have to do Taylor's theorem only to one term in t, but we can do it to two terms in x. So Taylor's theorem to one term in t gives us this, but we can also do it, but to two terms in f gives us df by dx at ti minus 1 xti minus 1 times xdi minus xdi minus 1 plus half d2f by dx squared ti minus 1 ai times xdi minus 1 squared, where Si lies between ti minus 1 and ti, and ai lies between xi minus 1 and xi. Okay, and I don't know which is bigger out of these two, so that's why I wasn't able to write this as an inequality. Okay, so this is just Taylor's theorem. It's a slightly weird one because I've done it to one term in t and to two terms in x. But that's the best that I can do, right? Because if you remember the assumptions that I made on f, I assumed f was once continuously differentiable in t, and twice continuously differentiable in x. And that's all I know. So I can't put any more terms in because I don't know that f has 2 derivatives in t. I don't know that it has 3 derivatives in x. So this is the sort of the most detailed version of Taylor's theorem that I can use for this particular function f. Okay, now I'm going to give you 2 arguments. I'm first going to give you a completely non-rigorous argument, just to give you some intuition for Ito's formula. And this completely non-rigorous argument will hopefully help you to remember it. So if you need to kind of write it down in a hurry, you can use this completely non-rigorous argument. But then I'll prove it rigorously in the simple case. Okay, so if you're asked to prove it, whatever you do, don't write down the non-rigorous one. Don't tell other people the non-rigorous one. It's just to help you kind of understand the shape of Ito's formula, why it sort of has that shape, to help you sort of remember it, and then we'll do things properly. Okay, so here's this. Maybe I should draw skull and crossbones. Okay, so this is non-rigorous. Okay, so just a little health warning over here. Okay, so non-rigorously, if I look at the difference between these two, that's kind of df at t xt. That's kind of how I like to think about this. It's a small increment in f. What about this? Well, this is just df by dt, and this is a small increment sort of at t and xt. So if these get close to each other and close to t, we've got this, and this becomes a sort of dt. Here we've got a df by dx. Again at t xt, and this is a kind of a dx. So this is times dxt, and then lastly we've got a half d2f by dx squared at t and xt, and this is a sort of dxt squared. Okay, so as I said, just ignore. I mean, this is just sort of a way to sort of remember it. When you see an increment in this, you kind of think dt. Increment in f, kind of think df, and increment in this sort of think dx. Right, but we know what dxt was. This was this Ito process, and so we can replace this by yt dbt plus zt dt. So this is now equal to df by dt, dxd dt, plus df by dx, and here we had yt dbt plus zt dt. That was our choice of x. That's how we defined x at the beginning, as this Ito process which had this property. And then lastly, half d2f by dx squared. And again, we replace this by yt dbt plus zt dt squared. Okay, so let's now look back at the statement of Ito's formula that we were trying to prove. Well, on the left-hand side, we had dft. That was fine. On the right-hand side, we had a yt df by dx dbt term. So that one's fine. We had a zt df by dx dt term, so that one's fine, and we had a df by dt term, so that one's fine as well. And there was one more term, which was half d2f by dx squared, yt squared dt squared. Okay, so we somehow need to argue that this bit is going to look like that. Well, this is where I get really, really non-rigorous. Okay, so what happens if I look at yt dbt plus zt dt and I square that? Well, I get yt dbt squared plus yt squared dbt squared yt zt dbt dt plus zt squared dt squared. Okay, and the idea is I want everything to be roughly of the size dt. If it's smaller than that, then I don't need it. And so if dt is very small, this is even smaller. So that bit's going to be close to 0. This is dt times dbt is small as well. So it's something small times something even smaller. So this bit's going to be approximately 0. And so I'm left with this. And so we get the form we want if we can identify dbt squared with dt. So get formula by identifying dbt squared with dt. Okay, and I said this is the bit where I'm really being non-rigorous. What I'll do now is when I prove it rigorously, you'll see that essentially this is what's happening. That small increments in bt squared essentially become small increments in t. But you know we need to actually prove that. So this bit here as an aside is just here to sort of help you remember how to rederive Ito's formula. So if you can't remember the exact expression of the formula, do the Taylor's theorem to two terms, and then just sort of observe, well, this is kind of a dt, this is kind of a dx, this is the dx squared. And then lastly, the only thing that you need to remember is essentially dbt squared becomes dt. Okay, so that's the way to remember it. Now we're going to actually prove it. And I'm just going to do it in the very simple case. So in the case where my process xt is just Brownian motion, and my function f only depends on one variable. So I'm just going to prove it rigorously in the very simplest case, but the other proof will follow. I mean, the full generality proof follows in almost exactly the same way. Okay, so we'll do the rigorous proof. In simplified case, when we have f of tx is just equal to f of x, and xt is just equal to bt. Okay, so using the Taylor expansion and the telescoping sum, we get that f of bt is equal to f of 0 plus the sum from I equals 1 up to n of this increment that we get if we pull that over to the left-hand side, which is equal to df by dx at bt I minus 1, bti minus bti minus 1, plus this term's not going to be there. So this term's not going to be here because we have no dependency on t. That's the bit I've just written down, but x is replaced by b. And now we've got this second term over here. So half d2f over dx squared at this value ai times bti minus 1 squared. Okay, so that's our expression. Well, this is exactly the approximating sum for a stochastic integral with respect to bt of a simple function given by this, and this approximates df by dx at b. And so this converges in L2 to the integral from 0 up to t df by dx of bs, dbs. That's exactly how we constructed our stochastic integral, was essentially as a simple process. This is the integral of a simple process, and so that converges to that. Okay, and the key point is it's mean squared convergence that we've got over here. What about this bit over here? So let's analyze the second term. So since d2f by dx squared is continuous, we can show that this has the same limit as if ai was replaced by bti minus 1. So integral from, sum from I equals 1 up to n d to f by dx squared of ai minus, let's just make life easier, let's just use double primes. Okay, so f double prime of a minus f double prime of bti minus 1 times bti minus bti minus 1 squared tends to 0, and again this is in L2. Okay, so you need to do a little bit of work here, but essentially we can pull this out and replace it by the maximum, which will converge to 0 by continuity. Well, we need this to be continuous, and bt is continuous as well. So because of that, this term is going to tend to 0 as the increments go to 0. And what we're left with is this sum over this, and this was just the expression for quadratic variation. So that's going to converge to t, which is finite. So we've got something tending to 0 times something tending to t, and so it goes to 0. Okay, so instead of having this ai, which is a little bit awkward because we don't really know what its value is, we can replace it by bt, ti minus 1. So that's okay. Also, we want to show that this over here converges to this sort of Riemann integral if we had this just replaced by ti minus 1. So also, we know that the sum from I equals 1 up to n, f double prime of bti minus 1 times ti minus 1 minus ti converges to the integral from 0 to t f double prime of bs ds. This is just Riemann integral. Okay, so if we had ti minus 1 here, rather than bti minus 1 squared, we'd be finished, right? But we haven't. We've got this, and so that's the last step that we need to do. So okay, so it remains to show that the sum from I equals 1 up to n, f double prime bti minus 1 times bti minus 1 squared minus ti minus 1, that this tends to 0 in L2. Okay, so if we can show that, we're finished, right? Because we had this expression here. We've shown that this can be replaced by, we can replace the ai by bti and it doesn't change. because these two converge to 0. And if this holds, that tells us that we can replace the bti minus 1 squared by ti minus 1. And then we know that we have the Riemann integral convergence. Okay, but this looks almost exactly like the proof that we used when we were studying quadratic variation, when we were trying to show that quadratic variation of Brownian motion was given by t. We had an expression that looked just like that, and we showed that its variance converges to 0. So in other words, it converges to 0 in L2. Now we've got this bit in front, but it turns out it doesn't make any difference. And so exactly this, or almost exactly the same argument as we used to show quadratic variation was that the sort of variance of this quadratic variation sum tended to 0, exactly the same argument works in this case. And so, so very similar, this follows. By a very similar argument to that used to show that variance of Q and T tended to 0. Okay, and that sort of finishes it. Okay, and it's precisely this step over here saying we can replace this increment squared by this increment. That's the rigorous version of what I've written down over here. So when you just want to have a way of remembering Ito's formula, just feel free to, every time you say dpt squared, just replace it by dt. Why can you do that? The reason you can do that is because you can show in L2 expressions that have this increment converge to expressions that have this increment. Okay, so that sort of gives you an idea of the proof of Ito's formula. And as I said, you can do it in the more general case. You've just got a few extra terms to deal with, but all the extra terms just converge to Riemann integrals, so they shouldn't cause any problems. Okay, any questions on what I've done so far? Okay, so I think we'll just break now until 1:15. Okay, shall we get started again? Okay, so I just wanted to write down what I showed you. In a way, was the most useful version of Ito's formula in one dimension, but we can actually extend it to higher dimensions. So instead of just having a one-dimensional Ito process, we can have a d-dimensional Ito process. So a d-dimensional Ito process is just a stochastic process consisting of d components, where each of those components is themselves an Ito process. So each component satisfies this formula, and in this particular case, we want the Brownian motions to be independent. So each component has an independent Brownian motion, and in that case, we can write down a version of Ito's formula for any function f, which again has a t variable on the non-negatives, and then it has d real valued variables, and as before, we want it to be once differentiable in the t variable and twice differentiable in each of the r variables. And in that case, again using this differential notation, so again immediately in your head turn this into the integral form. We've got the stochastic integral part, which has exactly the same form as before, except before we just had one term like this. Now we need to sum over yti df by dxi for all the values I equals 1 up to d, and each of these comes with a different dbt because these are all independent. So our stochastic, we have stochastic integrals, we have sort of d-stochastic integrals, each one with an independent Brownian motion, and then we've got our big dt expression, and again we pick up a component corresponding to each of the Ito processes, and again we have quadratic terms, and again one quadratic term for each of the processes, and the proof is similar. So proof is similar to before, but there's one extra thing we need to worry about. The sort of main difference is need to show that we get terms sum from I equals 1 up to n d2f by dxk dxj dxk Okay, so what you'll do to prove this, as I said, it's very similar to before. You need to use Taylor's theorem, but this time you're using a d-dimensional version of Taylor's theorem. And if you use the d-dimensional version of Taylor's theorem, you end up picking up these cross terms. You end up picking up terms that f is differentiated with respect to both xj and xk. And they have these increments that they're multiplied by. And so we need to show that the contribution from this tends to 0 in L2 as before. Okay, so that's the main difference, is that you need to worry about these cross terms. And what makes it work is precisely the fact that these BTIs are independent. We can generalize again to a version of Ita's formula where they're not necessarily independent. In that case, these cross terms will appear in this term. So we can say, we can do further generalization. Where the BTI are not necessarily independent. Are possible, but in this case the cross terms are no longer 0. So you will end up with terms in this expression which depend on these second order derivatives with respect to two different variables. But the cross terms are no longer 0. Okay, so I won't bother to write that down, but again, if you look it up, it'll look very similar to this, just with some more terms like this.
There is something strange with the notation here. Probably x should be with indexes t or I.
Oh, sorry. Yes, absolutely right. Sorry. These are i's.
Probably j and k also.
Yes. Yep. Sorry. Absolutely right. Yeah. Is that right now? Yeah, that's what it should be. Yeah. Thanks for pointing that out. Okay, so here's a useful corollary. So this is the stochastic integration by parts formula. So suppose that xt1 and xt2 are eta processes satisfying dxi is equal to yti dbt plus zdi dt for I equals 1 and 2. And notice here we've got the same Brownian motion for both. Okay, so this is important. Then let ut be a function f of t and xt1, and vt be a function of t and xt2 for fg in C12. Then we can talk about the UT-VT in differential notation. So what's UT-VT equal to? Well, it's UT dVT plus VT dUT plus YT1 YT2 df by dx dg by dx dt. Okay, so what we've essentially got is, and again, this is in differential notation, so in your head, immediately turn this into an integral form. That UT-VT is equal to U naught V naught plus this integral plus, with respect to dVT, which, plus this integral plus this integral over here. And when we've got dVT and dUT, you need to use Ito's formula if you want to express these two in terms of dBT and dt. Okay, so I've sort of grouped it together in this way, but we have an Ito's formula expression for this and an Ito's formula expression for this that you can substitute in if you want the full decomposition into a stochastic integral and a Riemann integral. Okay, but why did I leave it in that form? Why did I leave this as dVT and dUT? Well, because if I remove this bit over here, this is exactly the stochastic integration by parts formula that you know. So this is just very, very familiar. This is exactly what you would have known before. But as before with everything to do with stochastic calculus, we pick up this extra term. And in this case, the extra term picks up a coefficient corresponding to each of the yi's, a derivative corresponding to each of the yi's. And in fact, this extra term is essentially kind of this form where if you've replaced f by the product of sort of f and g, you're essentially getting this this expression over here. And the reason that this term has survived in this case was because the BTs were the same in both cases. If the BTs were independent, then that term would have gone just by this formula over here. So if the BTs are independent, we just have our old integration by parts. So if you've got two independent Ito processes, then integration by parts works the way it does. But if they both depend on each other, because they're driven by the same Brownian motion, then we pick up this extra term here, which is a sort of cross term involving the derivatives of both of them. Okay, and again, the proof, I'm not going to do the proof here, but it's an exercise on the exercise sheet, so please do have a go at this. On the exercise sheet, it's just in the simplified case when xt1 is equal to xt2. Okay, so that's something for you to do on the exercise sheet. Okay, so let's look at some more examples. Okay, so we're just going to go back to sort of 1 + 1 dimensional case and just let f of. So I'm just going to show you. I mean, we've seen already how powerful Ito's formula is in order to solve stochastic integrals. But what I'm going to show you is actually it's very, very useful for other things as well. And so in this case, let's consider ftx being e to the x minus t over 2, so a perfectly nice function. Then what happens if we just calculate the partial derivatives? So df by dx, it just stays unchanged. df by dt, and which is also equal to the second derivative, and df by dt is just equal to minus 1/2 e to the x minus t over 2. Okay, so let's feed this all into Ito's formula. So that tells us that d of e to the bt minus t over 2 is equal to, well, the df by dx term, so e to the bt minus t over 2 dbt, plus the df by dt term, so minus 1/2 e to the bt minus t over 2, plus 1/2 of the d2f by dx squared term, so e to the b2 minus t over 2 dt. And then we know something nice has happened. These two cancel each other out, and so we're just left with this is equal to that. What does that mean? So I've got that this can be written just as a stochastic integral. Let's just say this. So equivalently, e to the bt minus t over 2 is equal to, well, this value at 0, which is just 1, plus integral from 0 up to t e to the bs minus s over 2 dbs. Okay, what does that mean if I can say that this can be written like that? It's a martingale, right? So if you remember, well, if you did one of the previous example sheet questions, or in fact, I think I did this in the notes, we showed that this was a martingale before, right? And it was a bit of a pain to do it. We basically, we first had to check, obviously, adaptability and integrability. But then the main difficulty was we had to check this martingale property. So we had to look at this conditioned on fs, and we sort of subtracted bs terms, and we used all our properties from our conditional expectation thing. We pulled out measurable bits. We used independent bits. We used properties of exponentials of Brownian motion. It took a lot of effort to prove that this was a martingale. One line with Ito's formula. Okay, and so this is the sort of second use that I really want to emphasize is if you want to show that something's a martingale, which you might want to do so that you can use nice theorems like the optional stopping theorem or some of the martingale inequalities, you've got two choices. You can either do it by hand or you can use Ito, and in general, using Ito is super quick. Just for free, just calculate 3 derivatives, get some cancellation, and straight away. In fact, you don't even, well, I guess you need to calculate that one to get this one, but you really only need to calculate the drift term, and if the drift term is 0, then we know it's a martingale. Okay, so that's the sort of second use, and on the exercise sheet, there's a few examples to check.
If the drift term is not 0, then it can be martingale, right?
It can't be a martingale, that's right. Yeah, so if the drift term is non-zero, it's not going to be a martingale. Because straight away, if you take the expectation, this is going to have expectation 0, and so conditional expectation, whatever you have here is not going to be typically conditional expectation 0. I can't think of any examples where you're, in a slightly weird situation, I guess if what you got here was somehow independent of everything else, it would be kind of weird. If this is going to be a function of Brownian motion, which is non-zero, then it's not going to have conditional expectation 0. So this term is in fact, no, I stand by what I said. Yeah, this has to be non-zero to be a martingale. So yeah, that's what you need to basically do is compute the drift, and if the drift is 0, it's a martingale, and if the drift is non-zero, it's not going to be a martingale. Okay, so let's just write that down. So hence e to the bt minus t over 2 is a martingale, and let's just remind ourselves, so this is very, very quick proof. very quick proof of this fact. Okay. Okay, so I just want to tell you now about stochastic differential equations. So let's go for this next this definition of what is a stochastic differential equation. So, which we're going to call SDE in shorthand. So an SDE is a equation of the form dxt is equal to mu txt dt plus sigma txt dbt. Yeah. Now what you'll notice is different from before. So we've still got a stochastic, so again, just in your mind, turn this into an integral form. We've still got a stochastic integral and a Riemann integral, but the problem is x appears on both sides. So x is sort of an unknown in this equation. And so it's a genuine equation because it's got x on both sides, and so you want to know whether you can solve this. So can you find some variable x which satisfies this equation? So so here, as usual, bt is Brownian motion, but the key point is that xt is the unknown process. Just underline that. And the function mu of tx is called the drift coefficient. And sigma tx is the diffusion coefficient. Okay, and there's a special case here, which is if sigma is identically equal to 0, then we just have a standard ordinary differential equation, which you should be familiar with. So if sigma is identically equal to 0, we just have or ODE. Okay, so what does it mean for something to be so it's an equation, so it's got a solution. What does it mean for something to be a solution? So a process xt is I'm going to tell you what a strong solution is, and I'm not going to tell you what a weak solution is, but I'm calling it a strong one just so that if you come across a weak one later, you'll sort of realize, well, it's not the same thing. But this is a strong solution of the SDE. With initial condition x0 if for all t greater than 0, the integrals integral from 0 up to t mu s xs ds and integral from 0 to t sigma s xs dbs exist, and we have that xt is equal to x0 plus integral from 0 up to t Okay, so I can't tell you how to solve a stochastic integral, but I can tell you how to tell if you've got a solution to one. Okay, so how do you tell if you've got a solution to one? Well, first of all, these integrals need to actually make sense. So these coefficients need to satisfy the sort of moment properties and measurability properties in order for these stochastic and Riemann integrals to be defined. And then once you know that these make sense, if you add them together plus the initial condition, that must recover your process xt. So if the left-hand side is equal to the right-hand side, then you have a solution. All right, and in general, it's pretty hard to solve stochastic differential equations. I mean, in fact, it's pretty hard to solve ordinary differential equations. I mean, if you've done any course on ordinary differential equations, yeah, if mu is linear, you can solve it, but that's almost the only case. Even sort of having a quadratic expression in there, suddenly it's not all clear whether solutions exist. And so the stochastic one, I mean, if you can't solve this with sigma equals 0, then in general, it's very difficult to actually solve them. But you can sort of, in general, there are proofs of existence and uniqueness of solutions under certain conditions on mu and sigma. I'm not going to go into those here, but in general, sort of Lipschitz continuity is sort of sufficient for these coefficients in order to have existence. Okay, so this is all I'm going to say essentially about stochastic differential equations. The main point is to recognize when you have a solution. So if I give you a process x, you can check now whether it is actually a solution to this. So you basically need to evaluate this integral, and check that this equation holds. Okay, and the reason I sort of discussed this just after doing this example over here is that actually this example gives a very nice example of a stochastic differential equation. Okay, so what did we have over here? Well, we had, let's set xt to be equal to e to the bt minus t over 2. So well, then what have we got here? Well, dxt is just equal to xt dbt. So then xt solves the SDE. dxt is equal to xt dbt with initial condition x0 equals 1. Okay, so there's your sort of first example of a stochastic differential equation and its solution. And this is should be sort of reminiscent of if I let xt just be equal to e to the t, then I know that dxt is just equal to xt dt as an with x naught equals 1 as an ODE. Okay, so this is kind of the stochastic equivalent of that, and so we call xt the stochastic, so sometimes call xt the stochastic exponential. Okay, so yeah, there's your sort of simplest example of a linear SDE, and in this particular case, we have a solution to it. Okay, so I think that's all I'm going to say about stochastic differential equations. Has anyone got any questions on them? Okay, otherwise, and I want to just move on to the last section that I want to talk about, which is Brownian motion and harmonic functions. So now we're sort of bringing the course back to the sort of complex analysis that we talked about, that Stas talked about in the first few lectures. Unfortunately, it looks like I might have to run a little bit over today, so hopefully you won't mind too much. But it would be good to get this information across. Okay, so new section, Brownian motion and harmonic functions. Okay, so I'm going to start off just by recalling the Dirichlet problem. Okay, so let D be a connected open set in RD with smooth boundary. Partial D, and let some function phi from the boundary to the reals be continuous. Right, the solution to the Dirichlet problem is any function h in C2D intersect CD bar. So what do I mean here? I mean it's twice differentiable in our domain D, and it's continuous in the closure of D, satisfying the Laplacian of h is equal to 0 in D, and h is equal to my function phi on the boundary dd. Okay, so this is all revision from the first lecture that, or first or second lecture that Stas gave. He will have defined the all of this, and in particular, this is the. Are you all happy with this notation? Anyone not know what this means? No, you're all happy. Okay. Okay, so for any z in our domain, let Btz be a d-dimensional Brownian motion. So remember, that's all components are independent Brownian motion, and this one's going to be starting from z So what do I mean by that? Well, it means I can write btz is just z plus bt. If that's just a standard d-dimensional Brownian motion, I'll just shift everything by z. So it's a z there. Okay, and I also want a stopping time. So, and let t be the first time greater than or equal to 0, such that btz hits the boundary d. Okay, so here's my picture. Here's my domain d. Here's my point z. And what I do is I have a sort of, in this case it's two-dimensional, so I do a two-dimensional Brownian motion starting from z, and it sort of wiggles around until it first hits the boundary, and so this is b at time, btz at time t, the point that it first hits the boundary. Okay, so here's our theorem. So for each z in the closure of D, set h of z to be the expected value of phi bz at t times the indicator function that t is finite. Okay, and if h is locally bounded, then it is a solution to the Dirichlet problem. Okay, and in most cases, this hitting time t is actually finite, and so this sort of reduces to that. And again, if you recall from Stas's lecture, he will actually given you this formula over here. He'll have explained. He wrote down in that lecture that this was one way of solving the Dirichlet problem, and it sort of makes sense because the formula makes sense. At this time t, this is on the boundary, and so phi is a function defined on the boundary, and so this makes sense over here. So we basically run it until it hits the boundary, feed it into the function phi, take the expectation. This depends on z, depends on the starting point of our Brownian motion, and it turns out that gives us our solution to the Dirichlet problem. Okay, so let's prove this. So suppose f is a solution. Right, then by Ito's formula, so by solution I mean a solution to the Dirichlet problem. So then by Ito's formula, we know that df of btz, this is the two-dimensional Ito's formula, and so we need to look at the partial of this with respect to each component times dbi, and we can actually just write this as the dot product of the grad of f at btz dotted with our vector of Brownian motions. So this is just the df by dxi times dbti summed up over I equals 1 up to d. Plus, if you look at the second term in our Ito's formula, this is precisely the this is precisely given by this expression over here. It's all of the second derivatives added up together at dt. Okay, so this is just two-dimensional Ito's formula that we saw earlier. So for two Ito processes, where those processes are just two independent Brownian motions. Okay, but we know that f is a solution to the Dirichlet problem. So in particular, we know that this is equal to 0. Okay, so this is equal to grad f times dbt. So this is since f solves Dirichlet. And so it's harmonic. But what does this mean? Well, this just means that it's a stochastic integral. It's a pure stochastic integral. It's got 0 drift term. And so it's a martingale. Okay, so hence f btz is a martingale. Okay, but martingales have nice properties, and in particular, one of the nice properties is the optional stopping theorem, and it sort of makes sense to use the optional stopping theorem in this case because we've got the stopping time kicking around. So by the optional stopping theorem, we know that the expected value of f at any bounded stopping time, so in particular let's just take t min with some function t just to make it bounded, is equal to the expected value of f at 0. But what happens when this is equal to 0? Well, this was a Brownian motion starting at z, and so this is exactly equal to f of z. Okay, but then what happens if we let t go to infinity? As t goes to infinity, this converges to t times the indicator function being less than infinity. And we know that bt lies on the boundary, and so f is equal to phi. So this bit converges to expected value of phi of btz times the indicator function t less than infinity as t tends to infinity. The right-hand side doesn't depend on t, and so that gives us and this was exactly h of z. So that sort of finishes our proof. Okay, so hopefully you can see there why this is now a sort of culmination of everything that we've done. We've used Ito's formula, we've used option stopping, we've used martingale properties, and combining all these things together, we've basically been able to write down very, very quickly a solution to sort of a d-dimensional sort of partial differential equation, which in general could be quite difficult to solve. Okay, so let's just quickly talk about harmonic measure. So here's a corollary. So suppose that H is a harmonic function on D, then H of Z is equal to the expected value of H of btz times the indicator function at t is less than infinity. Okay, so let's define harmonic measure, and we'll come back and see how this is relevant. So okay, so let's define omega as a measure depending on z by omega z of some set A is equal to probability that Brownian motion starting from z at this hitting time t lies in A for each measurable A subset of dd. Okay, so this is a measure on the boundary of our domain. And using this, I mean, this is just an expected value with respect to this random variable, and this is the probability distribution of this random variable. And so let's just give this a star. So using this definition of harmonic measure, we can write h of z is equal to the integral of dd h of y omega z dy. Okay, and again, this is something that Stas will have wrote in that first lecture. And again, now you can sort of see why it's actually true. Essentially, it all boils down to sort of Ito's formula, because if you have a harmonic function, the Laplacian is 0, and so the drift term is 0. So you have a martingale. Okay, and we call omega z dy the harmonic measure on the boundary of the domain as seen from Z. Okay, so you're standing at Z, and the way you see things is through Brownian motion, through Brownian explorations, and any Brownian motion starting from you, it sort of tells you how likely you're to see a particular part of the cluster boundary. Okay, so one thing in particular we can deduce from that is Brownian motion is symmetric in all directions. Okay, so this is an exercise. This isn't on the exercise sheet, but it's one that you can just do for yourself, is that RBT has the same distribution as BT if BT is d-dimensional Brownian motion and R is d by d matrix and it's orthogonal. Okay, so that means that in particular, any rotation applied to Brownian motion still has the same distribution as Brownian motion. So if we know that Brownian motion is symmetric in all directions, we know that the harmonic measure on any ball around a particular point is just the uniform measure on that ball, and so hence h of z is just equal to the integral over the boundary of any ball centered at some point z, uy day for all balls brz which are contained in D, where dA is normalized surface area measure. Okay, so this is the sort of mean value theorem. So that U should be an H. So if I have a harmonic function, its value at the center of a circle is the average value that it takes all around the circle, and that holds in any dimension. Okay, just want to do one more theorem and one more example if I can. Hopefully I can do that in the next 10 minutes. Should I just ask, any questions on harmonic measure? Any of that not make sense? But as I said, it's all just boils down to the Laplacian being 0 means the drift term in Ito's formula is 0, and everything just follows from that. That's the key property to take away. Okay, so this is a very, very useful theorem. This is Levies' characterization of Brownian motion. So suppose that W is a continuous martingale with quadratic variation W equals T, then WT is a Brownian motion. Okay, and this is extremely powerful because we don't need it to be a Gaussian process, right? All we need is it's continuous. That's absolutely critical. It has to be continuous. It has to be a martingale, and the quadratic variation at time t is exactly t. And just given those three properties, we immediately know that WT is a Brownian motion. And this really is a very useful way to sort of recognize Brownian motions because you can show something's, I mean, generally you know something's continuous. That's not so difficult. You can use Ito's formula to very quickly show something's a martingale. And once we've got an Ito decomposition, we can compute the quadratic variation as well, because we know it's just the integrand squared dt. So the integrand with respect to Brownian motion, that squared with respect to time. Okay, so once you've got Ito's formula, it very, very quickly allows you to tell whether something is a Brownian motion or not. Now I had wanted to prove this today, but I think I'm going to just I think I'll just put the proof up on Moodle, and then you can read it. You can read it for yourselves. I think I'll just go straight to just the final example in light of shortage of time. So proof will be notes on Moodle. Okay, so I'll put that up in after the lecture. So here's an example, and this is the last example of the course. So suppose that Bt is a complex Brownian motion. So remember, that means the real part and imaginary part are independent Brownian motions. And suppose that if constant domain D to C is a conformal map, then f of Bt is a time change of Brownian motion. And just need a little bit careful here. It's defined up until Bt leaves the domain D. Okay, so this again, I think Stas mentioned in his lectures that essentially this tells us that Brownian paths are invariant under conformal transformation. So if I have some pretty weird process like this, and I start a Brownian motion, and I have a conformal mapping that turns that into the disk, let's use a different color. So that's my Brownian motion BT. And under F, this maps into something a little bit different. So this is F of BT. What this theorem tells us is that this here still has the same path as a Brownian motion. So the time change is different, but in particular, the hitting point of this on the unit circle is the distribution of a hitting time of a standard Brownian motion starting from that point on the unit circle. And that's a very, very useful property, and we'll certainly use that again when we start looking at some of these random growth models. Okay, so let's just see how you prove that just in a couple of minutes. So suppose that, okay, so proof. So suppose f of x plus iy is equal to uxy plus I times vxy. Then by Ito's formula, we know that du at bt1, bt2, the two components of this complex Brownian motion, is du by dx db1 plus du by dy dbt2, and the key point, this is plus 0 times dt, and this is because u is harmonic. So we know that real and imaginary parts of complex functions are harmonic, and so the Laplacian is 0, so the drift is 0. Okay, so that means that u is a martingale. It's continuous because it's just a continuous function. So u is a continuous martingale. Well, what's its quadratic variation? Well, we know what its quadratic variation is. It's just going to be the squares of the integrands against this, and the cross terms are going to be 0 because these are independent. So with quadratic variation, which is just equal as it's the square of this plus the square of this dt. Now, the square of this plus the square of this is just the modulus of f prime. So this is just integral from 0 up to t modulus of f prime of bs squared ds. Okay, so there's our quadratic variation. And we can do exactly the same thing for V. The real part and the imaginary part of analytic or conformal mappings behave exactly the same. So similarly, this holds for V. Okay, now let's define this time change. So let tau of t be equal to the first time s, such that this quadratic variation of u is equal to t, and this is exactly equal to the same if we replaced u by v, because the quadratic variation only depends on the function f. So okay, so we've got this time change, And well, what does that mean? Well, this is a genuine time change because these are strictly increasing. So because the quadratic variation is strictly increasing, because the derivative is non-zero, because it's a conformal mapping, this is a time change. So since quadratic variation, so it's a one-to-one transformation of the time variable. This is a time change. And it follows that u of b tau of t at 1 and b tau of t of 2 is a Brownian motion, and this is I'm using Levy. Okay, because we know it's continuous, we know it's a martingale, and because of this time change, the quadratic variation of this time changed quadratic variation is exactly t, and so this is a Brownian motion, and similarly for v. And finally, just to finish it off, we need to show that these are independent, but this just follows from the Cauchy-Riemann equation, so I'll leave that as an exercise. So and this is exercise, and use the Cauchy-Riemann equations. Okay, so that's sort of where I wanted to stop. I did want to get through this just to really sort of justify all of the results that Stas talked about in those first few lectures. And I said in particular, this conformal invariance of Brownian motion is extremely important. And likewise, this Levies characterization of Brownian motion is another very, very useful result. Okay, so any questions on any of that? Okay, so in that case, I think that's the end of me for the next few weeks. So next week it's going to be Stas, and he's going to talk about Loewner evolution. I think it's Stas for the next few weeks, next 4 or 5 weeks, and then I'll come back a bit later after that. Okay, thanks.